All right, welcome to the fourth part of the Solar Economic Investment Analysis web seminar series. We're going to really get into detail with the model today. We're going to be using the System Advisor model. We're going to run a scenario for a farm. We're going to look at the output and go through some interpretation. And then really where we're going to have some fun then is go into some optimization and saying, should that size of system be smaller or larger? Should we put it on a roof or on the ground, and some of those types of things. And we're going to be able to run some scenarios where we're optimizing, and we're going to show you how to use the tool in the process. So that's kind of our goal, is just to run a scenario today and really walk you through the process, kind of like what we did on day one, but with a little more detail and a little bit more showing you the ins and outs of the tool. This is the fourth part of our four-part series. We're going to have all four parts in recording for you and we'll send you a link to that soon. If you have interest in a written version, there is our seminar, our bulletin series, which essentially is broken up into 6 parts. We shorten that into 4 parts for our webinar, but all the things we talked about in our webinar are in this bulletin series, and you can have it in written format. We are going to use the System Advisor model, which is developed by the National Renewable Energy Lab, and it is updated by them. You can download that in Windows or Mac. And also, it's going to ask you to register. When you register, you can read their information on what they use that for. Basically, you're providing an email and some very basic information. I think it's just simply an email address, but then they're going to be able to see how much that's used, and they're going to say they want to know that so that they can write grants to the federal government to be able to try to support this program. So you can use it, I think, a number of times without registering, but eventually it will stop if you don't register. So it is a free software. All right, I'm going to switch us over to the System Advisor model now. Before I go to the System Advisor model, I'm going to go ahead and pull up kind of our project today and just give a visual overview of it. The project we selected today was a solar swine barn facility located in Ohio. Here is a general picture of what it looks like. And so we're going to run this through the System Advisor model. Obviously, this is a picture of one that's been built, but we're going to run it as a scenario like we're proposing it like it's not been built. And so this is obviously a roof mount, but again, because we're thinking of it as a proposal, we can make it a ground mount and put it next to it. We have a load profile, so we have some load data for this. In many cases, monthly load data is what we have available to us. And works fine. I'll show you how to use monthly load data. If you have hourly load data, which you might have to contact your utility to get, the System Advisor model can deal with hourly load data. And hourly load data is probably ideal if you have a rate structure with demand charges. It really can help figure out if that solar is going to work. If you have demand charges and you only have monthly load data, the System Advisor model is going to struggle with trying to see if that demand is ever reduced. So we can talk about that a little bit, but monthly load data is sufficient. Knowing what rate schedule you're on is going to be important. We're going to download some rates and look at them. This system we're going to start with is 25 kW in standard test conditions capacity. It's going to cost $2.20 per DC watt. That fits within the range of $1.70 to $2.70 from the larger commercial to residential rate or cost that we talked about on the day we talked about cost. It is roof mounted. This one is mounted in a slightly southeast orientation rather than due south. And so then we could compare if we put that due south as a ground mount versus in the southeast orientation. Some decisions we're going to have to make is, do we borrow the money or don't we borrow the money? Discount rate, inflation rate. We're going to go through our taxes and depreciation and some of those things. So those are all the kind of details we're going to need to fill out as we go through the System Advisor model, but I want to just introduce our project real quick for today. When you open up the System Advisor model, you're going to have, I'm just having trouble with my Windows for a second here. Sorry about that. You're going to have tell you what's going on, what's happening with System Advisor model. They're going to say there's an update, or there's going to say there's a meeting for discussions and things like that. This is kind of their little news feed. Sometimes it's fun because you might learn about a web seminar that they're going to host to go over new features. So that's kind of some of that. It also gives you an opportunity to open some of the most recent files that you used in the System Advisor model. What we're going to do is we're going to start a new project. Remember, the System Advisor model is powerful because it has all kinds of options. We're only going to use essentially one or two of those today. Photovoltaic, because this is a solar PV project. We're going to do PV watts because we are more interested in the economic modeling than we are the exact system design. Which solar panels are we using? Which inverters are we using? Remember, our installer is going to kind of come up with some of that information and deal with that. We don't need to. We're just simply trying to figure out some information about the general size and other things. So we're going to do PV watts. Because this is a behind the meter, we're going to call it distributed, and it's going to be a commercial. Again, you could choose residential. Really, the difference between commercial and residential is simply the depreciation. We see the depreciation tab when we use commercial. And then we're going to click OK. That opens up our System Advisor model, and we begin the process of filling out the tabs on the left-hand column. First thing we're going to do is download weather data. It's important to download weather data because we have to be able to figure out what is the production of this system at a particular location. Now, if you have an address, you can type a street address in there. If you don't have an address, use just the town. If you're within 10 or 15 miles of a site, it's likely going to, the weather patterns and climatic conditions are going to be pretty similar. So we're going to use Upper Sandusky, Ohio today, mainly because that's in Eric's neck of the woods. And we're downloading the default TMY file, which Eric suggested was the typical meteorological year file. We're going to download it to the library. It's going to go look for it. It found it and downloaded it. And it's going to ask me if I want to actually look at it. I don't, because it's just a bunch of data. And it's going to have selected this Upper Sandusky weather file. If I scroll down, I can kind of look, some of the numbers we talked about for the peak sun hours are here, 4 and 4.9, things like that. So we don't need to really pay much attention to those other than we have it highlighted. That's enough to go on to the next one. That's the weather file it's going to use. Now we get to select the system design, and this is where we have to go back to either the project file that we have. Maybe we also have kind of some idea of how big a system is, and if we don't, maybe we just make a crazy guess about how big it's going to be, and then we'll optimize for that later to figure out if we're right. So we're going to put it in at 25 kW right now. We're going to leave kind of some of these things standard. Standard solar panels versus the premium or the thin film. These are kind of design criteria things that we don't need to change. These are kind of middle of the road assumptions that are accurate enough. We are going to tell it whether it's on a roof or it's on the ground. And so an open rack is a ground mount, a roof mount is just that on the roof. In this case, we know that the tilt of that roof is 18 degrees and the azimuth with the direction it faces is 135 degrees, so in a southeastern orientation. We can change these losses if we want, but only if we really have information that tells us about changing those losses. So we typically leave these as standard losses. If we have time later, I'm gonna open this 3D shade calculator and show you how to use that, because this can be really important if you have some partial shading, and it can do some estimations of partial shading. In this particular scenario, that's a open area, there is no shading. We're not going to mess with this 3D shade calculator. The grid limits are really have to do with if you have rules within your state about curtailment and certain grid limits. We don't have anything in most states that we talk about, so we're going to just take that off or not mess with it. We're going to leave it as its default. We're going to go to the lifetime degradation. The lifetime degradation, remember how much those panels degrade over time when they're in the sun. And we saw a slide a few days ago that said it's really almost every solar manufacturer of the major ones is above better than 0.5% degradation per year or less. So it's better than that. And if we know what solar panel we're selecting, we can change that to meet that solar panel's degradation. Since we don't know, we'll leave it at the kind of industry standard at 0.5%. System costs. This is where you could, if you had a quote, you could do one of two things. If they detailed it to this level of detail, go ahead and fill in the different parts. That almost never happens. They're never going to tell you what is their labor, what is their overhead, and some of that, because they don't want to necessarily tell you their profit margin and some of that stuff. But we understand that there is one. So they're going to tell us a price that we're going to pay. And so we're going to simply zero everything on this line out in the whole thing. And by zeroing everything out in that whole thing, and we get to the end and we know we're zero because this bottom right-hand number is $0 per DC watt. Now we're going to go up to the modules and just put all the price in there. And the reason I do that is then I know where that price is. So when I want to mess around and do some scenarios later, it's all in that one line. So it's $2.20 per DC watt. And now that's there. So my gross cost is $55,000. Essentially, that's what I'm going to write the check for. And I know that my installer gave me a price that includes taxes, and that's why I removed the taxes even, because that was an after-tax cost, sales tax, if sales tax is in it. So it's all included. That's an all-in cost. And I've confirmed that there's no other costs. The electrical's covered, everything else is covered. I have seen projects that said, okay, this is the cost, but then there may be some extra cost if the electrician comes in high, and then you might put in some contingency or something like that. But anyway, we're gonna leave it at this for now. We're gonna move down to operation and maintenance. We introduced on day one that we can put operation and maintenance in at a single dollar amount per kW. So in this case, for our 25 kW system, $16 times 25 is $400 a year that we're planning for O&M. And if we did that across a 25-year time frame, that's about $10,000 in O&M across the 25-year life of this project. Although I think that number is conservative, there's other ways to put that in, and I'm going to demonstrate one of those now. We're going to lower this per kW rate down to $4. Put in a small amount of inflation because we're worried that price might inflate a little bit, and then we're going to put in some fixed costs. We recognize that the inverters are a failure point in systems and might need to be replaced. They're under warranty for 10 years, almost universally across all inverter types. Some are warranted for longer. So we're going to expect that in the first 10 years, if they go out, they're under warranty and we don't have any cost. But if they go out after year 10, we might have to pay for a few inverters. So what I'm going to suggest is maybe a third of our microinverters are going to go out. This is just rough numbers, but are going to go out during the second half of the life of our system. And so what I have is the 25-year life of our system. And I could actually change that to 25 values so that I see all 25. So I'm going to go here to year 11, and I'm going to put in $1,500. And I'm going to put in $1,500. I'm going to say that every year or two, we have to replace a couple inverters and pay the installer to come out and do that. And I'm going to do that 5 times, no, 6 times. And what that does is that actually adds my total O&M to approximately $10,000, the same as what I did before, but it just changes it a little bit. And I wanted to do that to kind of represent that you can put in O&M in different ways. I don't mind that O&M, you put in O&M lower than the $16, but what I don't particularly like is that when people say, well, there is going to be no O&M. Well, I'm sorry, it's likely there's going to be something, you know. So that's the 2 ways to put it in. Because I put it in both are going to show up for me in the model, both the $4 per kW and these $1,500 values that are in the second half of the life of the system. Now I'm going to go to financial parameters, and we're going to make some decisions. And Eric and I talked quite a bit about modeling this, and maybe I will just put it up for a vote. You know, give me a thumbs up on your camera using the thing if you want me to borrow the money, or if you don't, I'll pay cash for the system. Does anybody have a preference? Maybe you put it in the chat. Do you have a preference for paying cash or borrowing money for the system? He's saying borrow. A couple of people are saying borrow money. I'm going to open the chat box here. They're saying borrow the money. Okay.
Chat box is borrow. Yep.
Yep. Yeah, we're getting that. So let's go to this. To borrow money, we're going to use the debt percentage to borrow the money. And so it's 100% if we're borrowing all of it. We could do a portion of it, 60%, 70%, whatever we want. And if we're paying cash, we'd say 0. I'm going to borrow the money because you suggested that's what you want to see. I'm going to borrow that for a 10-year term at 4% interest. Although that's not maybe perfect for what exactly you could get, you're going to be able to know what you can get in your marketplace, but this is in the ballpark of what you can get. Sometimes states have low interest loans, and that may be a little lower for renewable projects. So, but a lot of times their term is maybe 10 to 15 years. So we'll do it for a 10-year term at 4%. I'm going to leave the inflation at 2.5% because when we look back at the past inflation, that's about what the inflation in the economy has been. And now we're getting to discount rate. It defaults at 6.4. Remember, there's all kinds of philosophies with discount rate. And it's challenging to say that one is right for a large group of people. I kind of lean towards putting a discount rate in that represents maybe what I might be able to make if I invested in another investment. I don't know if that's completely fair for everybody. Some businesses like to say this has more risk than another investment, so I'm going to increase the discount rate or something like that. But we'll leave it at, let's just make it 6%, round it off at 6%. Because that's a very conservative estimate of what I might be able to make if I invested money in an alternate investment. You can change the federal and state income or federal and state tax rates, income tax rates, if they're different. I'm going to leave these here because they're very close to what Ohio's is, and they're close enough for what we're doing. At the bottom here, we have insurance. We talked a little bit about insurance and reasons insurance might change. And Eric and I suggested that somewhere between 0.25 and 0.5% of the installed cost is a reasonable range. I'm going to leave it at 0.5 because I'm going to be a little conservative on this particular scenario. And then we'll run a scenario that's less conservative in a little bit, but we're going to leave that at 0.5%. Right now I have the property tax at 0 because we're going to suggest that this system is property tax exempt. And if it were in Nebraska, it is property tax exempt. In Ohio, it might not be. And so if we're not property tax exempt, we might say that this is 35% assessed value of a 4% tax rate, 4.02% tax rate. That it leads itself to about a 1% tax rate for property tax, but we'll again, we're being pretty conservative. So we're going to assume we have to pay some property tax on that system. Now we go to depreciation. Now, from the economic analysis standpoint, the depreciation, it doesn't really matter which ones you choose as long as you can take it. Because the total impact is going to be about the same whether I run it in one way or another, but the per year is going to be different. And so sometimes we want to be very accurate and say we're going to run a straight line depreciation for 10 years is one way to do it. Another way to do it is to run, we are allowed to get bonus depreciation at the federal level right now, so let's run it at bonus depreciation, in which case I'm just going to say 100% in year one. And so remember, this is in percentages. So I just simply put in 100 in year one, and I'm going to take 100% bonus depreciation in year one for federal and a 5-year makers depreciation at the state level. And so I can put in different ones. But again, the overarching impact is the same no matter which one I choose, but the per year numbers look a little different when you choose which ones. Incentives. I'm going to be very conservative on this version, and then I'm going to show you some less conservative numbers in a little bit. But to be very conservative, I'm really only going to say, this is a farm, it's a business, I'm going to get that federal tax credit. There's really no other incentives that I'm going to get. When I run another scenario, I will run with a REAP grant and assume that I maybe got that REAP grant, and I would put that in down here, but I'm not going to put that in at the moment. I'm just going to be very conservative. So that's all the incentives that I'm going to get is the federal tax credit, which is what most people can get unless you're a nonprofit. And now we're going to add in the electrical rate schedule. To add in the electrical rate schedule, the easiest thing to do is initially search for rates on the OpenEI database, which is integrated into the model. And the second thing to do is actually pull a rate schedule from your local utility and double check it. So in this case, it's going to communicate with the OpenEI database, and I'm going to filter by filtering my my utility. So Ohio Power is the utility for this particular project. I'm going to tell it to show me active rates only. And for this particular one, I'm going to, if I know which rate it is, I can select it. I'm going to tell you that if you're in a deregulated marketplace or you want to run the bundled rate, if you want the full rate schedule, because if you run an unbundled rate, you only get part of it because you're only getting the part that pays for transmission, not the part that pays for energy. So I'm going to use the general service time of day rate bundled. I'm going to click download and apply rate. It's going to tell me that it applied. Now I'm going to look at that rate schedule and see how it looks, see if it makes sense to me. So what I have is a 2-period, 3-tier rate structure. 2 periods, those 2 periods are simply at night and during the day. Period 1 is at night, period 2 is during the day. On weekends, it's all just period 1. The tiers are depending on how much energy I use in a particular billing period. For the first 2,000 kilowatt hours, it's 10.5 cents. After 2,000 until 15,000 is 10.4. And after I've used 15,000 and greater for large users, it goes down just a tiny bit, 10.42 from 10.48. In during the daytime period, the rate is about 13.87 to 13.8 cents across the year. So it doesn't change a lot in these tiers, but that would be the rate schedule it is. Now, I'm also going to look, do I have a demand charge? So I can scroll down and look at the demand, and it is enabling demand charges, but there aren't any demand charges. The charge currently is 0. So in a little while, if we have time, we'll run one with a demand charge. But right now, there isn't a demand in this rate schedule. And we can kind of interpret that as well by looking at this. These costs of electricity are fairly high. And so they likely include the demand within that rate. If this had a demand rate like $13 per kW, this might be maybe 5 or 6 cents. Because again, we're paying for the electricity in two different ways, both energy and demand. In this case, we're only paying for it one way, so it's going to be a little higher rate.
John,
Go ahead, Eric.
just a quick side note. Sometimes people think, well, why demand charges? And just, I don't know that we've ever discussed why they exist, and not that we need to spend a lot of time on it, but it's basically the idea that, the utility has to build the infrastructure, the wires, the transformers, to meet your maximum demand at any one point in time. And so, if you have a real high spike that only occurs just, for a short period of time, it's wasting a lot of, additional cost into overbuilding that infrastructure. So just FYI.
Yeah, thanks, Eric. Which of these metering and billing units you want is going to be really important for you to be able to select the right one. And this is based on the current net metering law in your state. If you had kind of an annual net metering, like we described on our net metering day, you would pick this top one. If you have monthly net metering, the second one is the one you want. If you're under PURPA, where you don't have net metering in your state by law, but you're under the federal rules, you click net billing. These are all behind the meter systems. If you end up being not behind the meter, you have the solar's on its own meter separately, maybe you'd be on a buy all sell all rate or something like that. But under the behind the meter scenarios, these top three are really the most important. If you're curious what one of these means, you can always click on the help menu in the upper right, and it will bring up, actually you're not seeing this probably, it probably opened in a different window, but it will bring up the descriptions of everything that is on that page. So it'll define all of these things in detail, as well as some of these other, the annual escalation, other things. Anything that's on this window, it will define in the help menu in good detail, including giving calculations and equations for how things are calculated. In our case, in Ohio, same as Nebraska, we're going to click on the net metering with dollar credits. And you'll see in a little lower that when I clicked on that, this sell rate popped up. And that's because the net excess generation, once I've subtracted out what I generated from what I used, I might have some excess. I over-generated in a month. What is that over-generation then worth? Then we go to the policy, and in Nebraska, they say it's worth avoided cost. In Ohio, it is the cost of energy in the marketplace. Eric, what's the definition that they say in Ohio? As I get these done.
Sorry, it wouldn't let me unmute. And it varies utility to utility, but most of our investor-owned utilities, it's going to be the retail rate for generation.
Thank you. The retail rate for generation, which is the cost of the energy component, not the total cost. You don't get paid for distribution and transmission. So that's a lesser value. So I'm going to put in 5 cents for that sell rate. And so that sell rate only kicks in when I overgenerate in a month for that whatever's extra that I overgenerated, the net. So I need to put that in. I can also escalate the electricity rate above inflation. So we already have 2.5% inflation. Now, does electricity increase faster than inflation? And this is where I can apply some of my maybe prognostication of the future. To be conservative, we usually leave this somewhere between 0.5% and 1.5%, or maybe 0 to 1.5%. I never go above 1.5% unless I'm being ultra aggressive. And then we got to be careful with what we come up with. So I'm going to put in 0.5% there. So just it's escalating just slightly faster than the economy. But remember, it's kind of, those two are addition. The economy plus this is kind of added together. So we don't want to put in 6%, or we're actually putting in, let's say we put in 2.5% here. We're actually inflating the cost of that electricity at 5% because it's additive to the actual inflation. Now we're going to go to the load. It's going to default to some load so that you can actually get numbers when you simulate the scenario, but these are numbers for some made up commercial system. What I've done is simply put my values in a Excel spreadsheet, and I'm going to copy them. And copying and pasting works in PCs in System Advisor model. It doesn't work in Macs. You just have to add them in one at a time. But if I want to edit the array, it's going to ask me for 8,760 values hourly. I don't have that. So I don't want to just edit the array. I want to normalize to the monthly utility bill data and edit those values. At which case I'll be able to go in and just paste in my numbers. And now these are my numbers. What it's done though, is it took my kilowatt hours in a month and converted that to a peak KW. So if I want to actually look at it, oh, you can't see it, it brings up another table, but I can actually look at the hourly values that it translated that into hourly data from monthly data. All right, we are ready to simulate. Are you ready to see our first values? We click simulate here in the lower left, and we're going to see that it's estimating it'll produce 30,660 kilowatt hours a year. Our levelized cost of energy real is 7.58. So we're already getting a little bit of a hint. Remember, levelized cost of energy is the cost of the system divided by how many kilowatt hours it generates in its lifetime, 25 years. And it's lower than our 10 cents that is the cost of our electricity. So this is a good hint that this is going to be maybe an okay investment. It's our first hint if this is going to be an okay investment. We move down and we look at the payback period because that's what everybody wants to know. 12.2 years. So the simple payback is 12.2 years. In this case, the simple payback includes O&M and insurance and things like that and all those costs. But when I discount that with my discount rate, the discounted payback is beyond 25 years. So now we're kind of in this middle of the road where the investment starts to look okay. When I look at levelized cost, the payback period looks maybe a bit higher than I wanted it to be. The discounted payback's not looking great. But now I go to and maybe the most important factor, if I'm comparing two investments, is the net present value. And the net present value is $7,300, suggesting that I am making over 6% on this investment. And if I'm comfortable with my discount rate, this should be a good investment. So I'm kind of learning a little bit about that. I can also find out how much did I save in year one. So I saved $3,893 in electricity in year one. So that's essentially my electric bill went down by that much in year one. And then of course, with inflation, every year it's going to change just a little bit. Let's look at some of these charts quick. This first chart is the production through the year. And you can see I do much better in the summer than I do in the winter. There's some different reasons for that. One of them that Eric and I talked about yesterday is that very clearly Ohio has cloudy, wet winters. And although I could change my tilt angle and try to optimize for winter, Ohio has cloudy, wet winters. And so it doesn't do as well in the winter as it does in the summer. And so if we did this in Nebraska, I would have a similar kind of bell curve shape production curve, but my winters wouldn't quite look as bad as his winters because we have more sunshine in the summertime or in the wintertime than they do. All right, let's scroll down just a little bit. We're going to look at this energy production. We're simply suggesting this is the degradation over time. That solar array produces just a little bit less each year. And in reality, it's going to go up and down a little bit because the weather and patterns and climatic conditions, the weather pattern each year are going to be a little different. But this is kind of that average of it's going to degrade over time slowly. This cash flow is kind of a fun one, and it's kind of interesting to interpret. So in year, let's say 0, when I first started, I had to, in some cases, sometimes there's a big negative because I paid cash. In this case, I didn't pay any cash. So I borrowed the money, but in year one, I got this big benefit. What's that benefit? That's the tax credit. So I got my tax credit back in year one. Then I started paying that off. I'm getting the value, but I'm paying more than I'm getting back in savings as I'm paying off that loan. Then after I get that loan paid off, now I'm just having savings. This back and forth is that $1,500 that I had in O&M, but you can see that my savings is increasing over time with my inflation rate and my increased cost of the electricity over time. So essentially, this doesn't necessarily clearly show the payback. This is the chart that could show the payback if I did this as a, depending on how I set it up, but this is just essentially looking at my cash flow over time. All right, now here's my favorite chart. My favorite chart is comparing the load to the electrical production from the solar. And what I'm looking for here is months that I overproduce. And in this case, August, I overproduced in August, but only a tiny, tiny bit. Because I only overproduced in August a tiny, tiny bit, that small amount right there, I got 5 cents for. But everything else throughout the entire year, I got full retail rate for because I did not overproduce during the month and I'm on a net metering rate schedule. So this to me suggests that number one, I'm getting retail rate for almost everything, but also that I don't want this system to be a whole lot bigger because as soon as I get it to be bigger, yes, I'll be generating more electricity, but then I'll have this month start over generating more and more. And I'm going to get 5 cents for that over generation. And my economics probably aren't going to look any better. So I've kind of really optimized my generation for this. And so let's just run a quick back and forth scenario really quick. Let's just make this system much larger and simulate. I made it 50. I doubled its size. And we're just going to go back and look at that chart, and then I'll flip it back. Now, yes, I generated a lot more and I have a lot more savings, but I also I'm getting hurt on the months where I'm over generating. And if I look at my payback's going to be longer because of that, 13.3 years. So I actually kind of hurt my economics a little bit by making my system large. So this is where you can start with whatever system size you want, but then what you want to do for maximum economic efficiency is simply reduce your system size until either you minimize the payback period or you're getting where you've minimized the number of months where you overgenerate. That's kind of your ideal payback. Now, there are situations where a farm or a business want to be known as 100% renewable. If you want to be 100% renewable, you're going to have to put up with some overgeneration on some months, and you're going to and maybe your economics aren't going to be quite as optimized. But again, if that's their goals, then they can balance their goals with the economic returns. So I'm not saying that you have to do a system of a certain size. It's just a matter of how do we optimize economics or balance that with our goals. All right. What I'm going to do now is I'm going to rename this scenario as conservative. And then I'm going to duplicate it by clicking duplicate. And I'm going to create another scenario that is aggressive. And I'm going to try to represent this second one as an aggressive. And I'm going to, by clicking on the different ones, I can actually, then I just copied, everything I did was already saved. But now I'm going to go through and change and make this an aggressive scenario. By making this an aggressive scenario, I'm going to change some of my numbers to say, you know, I don't think O&M is going to be quite that high. You know, I think that was an overestimated. I haven't seen inverters go out at that rate. And so I'm going to just reduce my values down on operation and maintenance. I'm going to go to financial parameters, and I'm going to reduce my insurance I'm going to reduce my insurance down to, instead of 0.5%, I'm going to go to 0.2%. And I'm going to say that I don't have any property tax, because, you know, I think that my state property tax is it's going to be exempt, or I'm just going to assume it's exempt because I'm trying to be aggressive on this scenario and make it look good, and just ignore that property tax exists. Some other thoughts on that. So I'm going to go to my incentives, and we're going to say, hey, look, I'm an installer, and I'm going to tell you that we're going to get this REAP grant. I'm going to fill out the paperwork for you, and we're going to get that thing. And that's 25% from the federal. We're in Ohio, and we know that we are going to get some.
John,
go ahead, Eric.
Not that I'm not suggesting that we model this, but maybe just to point out that it is a function that's available. So, you know, we talked about like the USDA REAP grant. That's if you are successful in getting that, you're going to pay income taxes on it, right? That's ordinary taxable income. If you don't pay income taxes on that, you need to reduce the depreciable portion of the system cost before calculating your 26% investment tax credit. So it's just kind of handy that it has those radio buttons there that'll automatically do that math for you.
Yeah, so you need to click on either it's taxable or you reduce the depreciable basis. So one of those two. And we're going to leave it as taxable in this case. But thank you, Eric, for pointing that out. In Ohio, we have SRECs, solar renewable energy credits. We're going to put in a value for those that is maybe in between what Ohio's rate is and Pennsylvania's rate is. We're going to say we're going to get $20 per kilowatt hour. Is that unit? That's not right, is it, Eric? It's $20 per megawatt hour. So then I need to move the decimal place 1, 2, 3. So I need 0.02.
There you go.
Watch your units. Units are real tricky in this sometimes, because I read that the SREC is $20 per megawatt hour, but I have to put it in now in kilowatt hours. So I had to move the units there. So,
and that's a good reminder in terms of these units. That's why it's so important. And John and I, even though we've spent a lot of time in this model, still, when we run something, go just kind of dissect the cash flow table and look at the numbers that are in your cash flow table. That way, you know, if you miss a decimal place somewhere, it's going to jump off the page at you, and you'll be thinking, wait a minute, what type of an incentive is that? And then you kind of go back and fix it. So just a good reminder for that.
I'll show you where the cash flow table is in just a moment, and that's a good reminder to do so. There's my utility. We're just going to assume that this utility that they're on, Ohio Power, even though they don't have this, have some sort of utility incentive, like mine here in Lincoln at $375 per kW of installed cost. Now remember, that's kW, and this one is in watts. So I need to, again, move the decimal place. So 0.750 in watts is the utility incentive in a dollar amount. So now I've got multiple incentives going on, and I'm assuming I'm going to get all of them. Again, I'm being aggressive. I'm going to kind of look at this as the ultra best case scenario. I get every grant there is available. My electricity rates, I'm going to leave the same, but I'm going to be a little aggressive. And I'm going to say that instead of 0.5% a year, I'm going to inflate that at 1.5% a year above inflation. So because I think we're going to retire some coal-fired power plants, the price of electricity is going to go up, and I need to be more aggressive with that.
And again, so think about what this is going to do behind the scenes. You know, John showed the charts that he was, you know, really liking with our showing that, you know, we were not necessarily over generating on that 25 kW system, right? So we were offsetting most of our energy at this 13 cents per kW or per kilowatt hour. And now we're assuming that it's going to increase by 2.5% inflation plus 1.5% energy escalation. So we're thinking every year this number, this value is going to go up by that percentage. And for a system designed like this, where we're basically using everything that we're generating, that's going to really impact your performance.
Great. We're going to click on load. We're not going to change anything there. We're going to click simulate. We're going to see how our aggressive scenario works out. Our aggressive scenario, the price levelized cost of energy is $1.5 per kilowatt hour. I mean, I'm already on board. Let's do it. We're going. This thing's getting built. Our simple payback, 3.5 years. Discounted payback, 4 years. Oh, I'm super excited about this. The net present value, $33,000. Again, the net present value only has to be above 0 to make this a good deal. And it's $33,000. I not only made all my investment back, I made an additional $33,000 on this system. This is really quite awesome. Now, it's really quite awesome, but we also maybe ran this as an ultra best case scenario. We may not have got all those grants and things, but again, it's kind of fun to run. And now we can kind of play with what is the absolute best it could look like and what's the worst it could look like. And I say worst, I was very conservative, feeling pretty confident in those numbers. And so 12-year payback, net present value of $7,000, discounted payback over 25 years versus the aggressive, which is really good. And the reason I ran the aggressive is you can lie to yourself with this program. And just like many installers are honest people, some are trying to be very sly salesmen, and they can tell you numbers that, hey, I could back up these numbers, but they aren't conservative, right? Go ahead, Eric.
And just hopefully with this workshop, our hope is that we've helped you understand, what some of those trigger points are. What are some of the variables that we, right or wrong, none of us know the future, but we have to identify a value for these variables. And I think hopefully this will help you figure out what are some of the questions you need to be asking if you see someone presenting you with a proposal for a 4-year payback. Okay, well, what was your energy escalation rate? Is it real or nominal? What are you assuming on your net metering terms? And, did you apply a discount rate for the time value of money? Hopefully you'll understand what questions you should be asking so that you can really understand, what it is that they're presenting with you or on that project.
Right, because you're never going to get two quotes that are identical, and you've got to kind of interpret them. And I don't blame an installer that maybe says, well, we don't know what the insurance is going to be, so we're not going to add insurance to our quote. Fine, don't add insurance to your quote, but just tell them that. And if you can, then you can kind of still interpret the difference between the two proposals. So try to figure out what's included in those proposals. Let's click on, we have these different things at the top that give us all kinds of options to visualize this data. I'm going to click on the cash flow, and we're going to visualize it from the cash flow standpoint. I'm just going to look at a couple of places. Here in O&M, we're paying $100 a year in O&M, but again, we're not actually paying this out. This is just a plan for what it's going to cost. And so if for the first 3 years, we don't actually have any expenses at all, but then here in year 3, my kid hits a baseball up and breaks a solar panel, and I have to spend $250 to get a solar panel, I have kind of planned for that operation and maintenance cost, right? So these are kind of the just projections that we're trying to add some value. Now, remember at year 11, we've got this $1,000 built in up here. And so these are where some of our other costs are coming in. And the total O&M and the total operating expenses are going to be the total of all those. So those are built in. I have insurance at $110 a year and increasing with inflation. And so we can start to see this. I like the cash flow because it kind of tells me, oh, I got an issue. I pulled this up and had these numbers be real big and went, oh, I didn't mean for that to happen. Maybe I left $16 per kW and included the fixed costs. All of a sudden, my O&M is overestimated. I can also go down and just try to figure out if, you know, am I overestimating or underestimating my my tax savings? And so I can kind of look at some of those tax savings with the federal income tax incentive, which is the federal income tax credit plus the depreciation that's spread out over the 10-year or the maker's depreciation. However that's worked out. I thought I put in the 5-year makers, and I'm seeing that spread out across 10. So maybe I have it set as a 10-year straight line or something. But again, that's where I'm seeing these numbers, and then I can try to interpret them. If you really are into numbers, I really encourage you that this is super fun to hit send to Excel with equations. You'll get an Excel spreadsheet with the same numbers, but then you can actually backtrack equations and figure out where all these numbers came from. And it really is enlightening to see how they did all these calculations at times. Also can help us interpret, did they include taxes on that or didn't they? You can figure that out. Okay, we're going to go back to the summary. Let's create one more quick scenario. I'm going to duplicate this one more time. I'm going to rename it, and I'm going to put this, I'm going to call this one most likely. So I'm going to have 3 scenarios just built: conservative, aggressive, and most likely. And so I'm building off of the aggressive scenario. So I've got to work my way back through and give myself a most likely opportunity here. So in this case, I'm going to edit this back to my 1500 because I like that one a little bit better. And so now I've got those put in, and so I like that a little bit better. My financial parameters, I'm going to increase this this insurance rate up to maybe, well, let's just put it at 0.4 because I don't think it's going to quite be 0.5, and I don't want, I think 0.2 is too low. Do they have property tax in Eric in Ohio? Should I add that back in?
No, commercial systems are exempt in Ohio from
commercial systems are exempt. So most likely I'm going to say it's going to be 0.
No property tax and no sales tax.
No property tax, no sales tax. We're good there. We're going to go to incentives. Now, most likely, I'd love to apply for this REAP grant, but REAP grants are really competitive. And I do encourage you to apply for a REAP grant, but they're real competitive. So I'm going to say most likely I'm not going to get it. The utility does not have this capacity-based incentive, though I am going to get in Ohio a SREC, but I don't think it's going to quite be $20. I think it's going to be $10.
Yeah, put it in at 10. Most recently, it was traded, I think, at like $9.50.
Yeah.
And then you could always add a small escalation if you think, okay, maybe over time that could increase. There you go. That's good.
So now I'm kind of more likely to happen here. I'm feeling more comfortable with these values. My bill escalation rate are aggressive. Let's put this in at maybe let's put it back in at 0.5%. I kind of like that as a lower escalation rate. We're all good there. We go to our load, we're not going to change anything there. So our most likely to happen scenario is this. And actually I got something else. No, we're okay. Because remember the first one, we were very conservative and we charged property tax, and then we know we don't have property tax. So our most likely in this case is levelized cost of energy, real to nominal, 5 to 6 cents, again, below what we're paying. So that's a good indication. Simple payback, 8.9 years, discount payback, 15.9, and net present value at 15,000. This is seeming like an okay project. Are these good enough for every farmer? No. Is it good enough for some? Yes. But now we have some better feelings about what is happening with this. So we went to the cash flow. We can look at it again, but we already looked at that once. So this is kind of the way I like to run these scenarios, and you can copy scenarios and make different versions and change different things. And so what I might do then I'm going to duplicate this one more time just to do something really quick because I think we're doing okay on time, but I'm not going to try to lose too much here. I'm going to rename this most likely, but with a demand rate. And I'm going to go show you how to change rate schedules so that you can build a rate schedule. So in my most likely with demand, instead of downloading a rate, I'm just going to build one. And knowing my rate schedule, because I pulled my bill, I know that I have essentially a two-tiered one-period rate structure. And so my one period, I've got to make my one period a true one period. So I've got to take all of this number that are 2 and make them into 1. So we're going to make those all 1s. So now I don't have 2s anywhere. It's all one period, but I have 2 tiers. And because it's a demand rate, what it costs to buy this electricity is not 10 cents. It's actually more like
5.289.
5.289, and then
0.5. I'm sorry.
Yep, no, I got it. I saw my mistake there. 52 cents would look really good.
Yeah.
Okay, so then as I use a lot more electricity, that price is going to go down slightly. So 0.05, I don't know, 159, something. So it goes down slightly, and that's what we saw. We're just making this up, but you're basing this on your electric bill. My sell rate is going to remain the same, but you can see my buy rate's way down. And that's because I have a demand charge that's going to make up for my transmission costs and things like that. So I'm still enabling the demand charges, but I'm going to put in a set demand charge per kW at $13.52 per kW. So depending on what my peak is at any given month, I'm going to be charged $13 per kW for that month. And I think that's the only changes I'm going to make because I'm most likely on a demand rate, and I'm going to hit simulate. And folks, it's not going to look that good. Remember, now most of my electricity is worth 5.5 cents rather than 10 to 13 cents. And it's hard to reduce demand with solar. So you're reducing it a little bit, but not a lot. And so if you're on a demand rate, the economics don't look as good. The levelized cost of energy still look okay, but our payback period and our net present value don't look as good because we're not getting as much for the electricity. And this is why Eric and I really focus on the idea of, if you're interested in an economic analysis, any one of these metrics, levelized cost of energy, simple payback, or net present value, any one of them is hard to understand the whole story of what's going on. But when we get all of them, we can start to see what's happening. And if you are on a demand rate, or if you end up on a demand rate in the future, solar doesn't work as well.
And again, if you're going to model a demand project, I really encourage you to work with your utility and try to get your load profile data on 15-minute intervals, 30-minute intervals, 60-minute intervals, whatever their demand rates are based off of. So however they're calculating it, that's really how we need to input it. Because that way, if you do that, then SAM has the ability to use the weather data and see, okay, when do we expect this system is going to be producing? And then they can overlay that with your sub-interval demand data and say, okay, well, this is when we know the facility is using energy. Is there an offset taking place or not? One, I guess, just to be aware, SAM will give you some issues if your weather data and demand data are not in the same interval. So if you're using 15-minute demand interval data on your load profile, you need 15-minute weather data and the resource profile. It has issues if you try and use 60-minute weather data with 15-minute demand data.
Very good. Okay, let's try to do some optimization here quick. And we're going to show you how to do some optimization. I'm going to go to my most likely scenario and use it as my base. Then I'm going to go to the lower left-hand corner and I'm going to click on Parametrics. And parametrics is just a way to run multiple scenarios at one time rather than changing one thing and writing down your answers and keeping going. So what I want to do is figure out which of let's go back to my system design quick. And I want to look at, I'm going to change it to 180 degrees because I want to look at the ground mount and I want to see if the ground mount, what is my optimum tilt angle for the ground mount? So I'm going to say I'm going to try to decide if a ground mount is going to be a better deal. And I want to look at if what is the optimum tilt angle for that ground mount. So we're going to try to optimize for that. So I changed to 180 because I want that to be my azimuth for my ground mount. Facing due south is usually the best. And so then I'm going to do quick setup because I'm going to do that'll allow me to put in a whole bunch of things easily. And I'm going to add, and I want to change the tilt angle. So I'm just going to type in tilt so it can find it. Otherwise, you can go and search around to find it. And it's going to say that my tilt is 18 degrees. But I don't know if that's optimum. So let's just run it from 18 degrees to 45 degrees in 3-degree increments, just for fun. And we're going to hit OK. And we're going to hit OK. And it's going to add in those numbers. What is my output? My output, I want it to be the production of the system, annual AC output of the system. Or let's just make it annual energy output of the system. I run the simulation. It runs all 10 of those right away without me having to change anything. And I can then say, look at the numbers to figure out which one is the highest. 32,654 is the highest number. So my optimum tilt angle is 33 degrees. I could run that in even tighter increments, but probably isn't as critical to be too tight on that. But if I'm going to build a ground-mounted solar array, I might pick a tilt angle of 35 because it's fairly easy to measure. You know, my scale has the big numbers are on 5 for tilt. So I might build that at a 35-degree tilt angle to optimize my system cost. Now, just for fun, now that I know that the optimum tilt is 33 or about 35, I go back to system design and I say, what if I have a 35-degree tilt angle at 180 degrees and it's an open rack system? How does that change my economics? And it actually helped me just a little bit. I was at 8.9 year payback. Now I'm at 8.6 because I produced 1,000, almost 2,000 more kilowatt hours through that system. So that's kind of fun. You can do some optimization in that way.
John,
go ahead, Eric.
Yeah, and at 13 cents a kilowatt hour, I mean, you're looking at, you know, $120 to $150 a year just for that. While it doesn't look like a big difference in that chart, well, guess what? That offsets your annual O&M.
And look at my winters. My winters look a lot better. They were much lower. Now that winter is looking a lot better because I raised that tilt angle and changed it to facing south versus facing southeast. So that ground mount may be a better deal for this particular application. Let's do some optimization of system size. Remember, we talked about that. Maybe you didn't know what system size you wanted, so we want to do some optimization of size. So I'm going to go back here, and I'm just going to turn off all my inputs.
One thing I have noticed just from experience as I look at proposals, John, it does seem that, you know, typically the mindset when someone's putting a proposal together is, we want to offset 80% of your usage, or, you know, it's often based on a percentage of usage, not necessarily we've designed this system size to maximize your economic return or your economic performance.
Right. So that's a good point. And in some ways, that's their way of trying to do it, but because you want to underproduce to get optimum economics, but we're going to do that in a little different way. So we're going to add the system nameplate capacity of the system, and it's 25, and we're going to edit that, and we're going to run it from 15 to 40 in 5-degree increments. So we've got these different system sizes in there. Now, the reality is that what we want to output then is our economic return numbers. NPV, we're going to get rid of our annual energy. We're going to put in net present value. And I also want payback. So I'm typing it in because I know that it pops up when I type it in. You can also search around for these and find them. So now I have NPV and payback as my outputs. My system size is that, but I also need another input, because one of the things that we learn, and from more experience than from reading, is that when you have a smaller system, it costs more per kW than a larger system. There are economies of scale. So I want to input the cost of the system change. I want to model that across a different thing. And remember that I put all my system costs in that module. So that system costs are all $2.20 per watt. But if that system size is smaller, it's going to cost more. So I'm going to say that's going to cost me $2.50 when it's small. And once I get bigger at 25, I go to 2.2. And then once I get larger, I actually get, I'm going to say I go to maybe 2.0. So they're $2 at that when I get larger. Maybe that largest one even goes below 2 and is at $1.80. And I know that because I've talked to my installer and he's modeled a couple different sizes of systems, and there's economies of scale. So I build those into this, and I'm going to run all those scenarios all at one time and see what's going to work out best for me. So in this case, I want to balance. I want to know that I have a positive NPV, and I do. But now that I have a positive net present value, really I want to go have the highest net present value at the lowest payback. And my lowest payback is actually going a little bigger. And so 7.2 years as I get larger, but that's because I got some economies of scale where that system cost me less as I got bigger. And so I may be overproducing a little bit, but maybe that's okay. And if I keep going bigger, 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 I might break it over and start to do that. And I could actually run that.
John,
so let's try that. Go ahead, Eric.
I think it'd be interesting to change the system size to 40 and look at your load versus production to see how much we're overproducing.
Yeah, let's do that. So now I'm looking at maybe convincing myself that I want a little bigger system. So I'm going to go into system design. I'm going to change that to 40 so that I can look at what the output looks like when I do that. I'm going to scroll down to the bottom. And again, that 40 is actually balancing pretty well. I have some overproduction in August, but I'm just barely overproducing in May. So I'm only overproducing in on 1 month. And so that's actually looking pretty decent.
Because when you're offsetting a unit of energy that you would otherwise pay 13 cents for, which, is a little bit high, but it's, that's a good value. If you can offset, 11 months out of the year, you're doing pretty good.
So I'm going to try to just recreate this a little bit. And then I'm just going to make all these bigger ones.
Just a quick reminder while we're doing some of these analysis, if you have questions that you want us to address, we have about 15 minutes left here. Go ahead and type your questions into the chat box.
Okay, and so I wanted to make that bigger to see what happened. And I got the economies of scale at 40, but after that, it didn't change much. So you can see that still 40 is ideal, and I actually start going up again in my payback as I get larger. So again, that run number 6, which is at 40. So this is where I can do some optimization with this model, and it's pretty powerful. So I'm going to do 2 more things on the model and I'm done, but I would rather answer questions if you have them. But what I'm going to do, I'm going to go back to simulate and go back to my thing. But on any of these, I can run reports. And I can create reports that are PDF reports so that if you're sending this to a client, let's say you're an extension person and sending this to a client, I can then create a report for an individual run of this and send it off to them. And it will put kind of a lot of the assumptions in, not all of them, but a lot of the assumptions in and the output. So that's kind of fun. You can run those reports. You can also save. I'm going to go ahead and save this. I'm going to file. I'm going to save it as, I'm going to call it March 2021 example. And I can save that to my project files and go back and look at it later. And so then when I switch to a different one, I don't have to lose that data. So now I'm going to open a project and I'm going to show you some shade modeling. And I'm actually going to open my house, I think, because my house has some good shade modeling in it that I want to show you. I have a small system at my home, as you know, and when I go through the system design, I didn't at first think I had any partial shading, and I didn't think that was going to hurt me. But then when I started to do some modeling, I recognized that I do have a little bit of partial shading, and it hurts me a little bit. I lose about 300 kilowatt hours to shading. So what I'm going to do, what I ended up doing is I opened this 3D shading modeling tool, and I ended up downloading a aerial image of my home. And so I have my house, but I also have my garage, and the solar is going to be on the south side of my garage. And once I did that, then I started, I went into the 3D scene and I started adding trees. And so I could create, let's say, a tree. That tree is obviously too big, but then when I go back to the bird's eye, I can edit where that tree is by pulling it around. I can edit how tall it is. It's only 20 in height. Its diameter is only maybe 4. And I can edit that. Its trunk height is, so let's go back to the 3D scene and see what it looks like. So I got kind of a weird looking tree over there now, but you can edit that tree to be whatever it wants. Now, what's interesting about this particular model is that, I'm going to delete that tree now because it's not there, but is that this is a unitless set of measures. So what I'm actually trying to do is create my garage and this tree in relative terms. So it doesn't matter that you put it in at X number of units, as long as you make them relative to one another. But here's where this is powerful. So I have this 3-dimensional scene now, and my eyeball, or your eyeball in this case, is going to be the sun. So the sun is going to come up in the morning, and it's going to be, let's say, the springtime day. So it's going to come across the sky kind of like this. You can see that, 6, 7 o'clock in the morning, that whole array is shaded. And then it starts to come out of the shade of that tree. And by maybe 9, 10 in the morning, I've got only partial shade. And then finally, by about 10:30, no more shade. For the rest of the day, and as the sun comes across the sky, the sun is your perspective. For the rest of the day, I have no shade. And so what it's going to do is it's going to calculate the whole year's worth of data and figure out what percentage of the year is that solar array being shaded by that tree. And that one tree is really my only problem. So I could delete every other tree on here. I just left them there for fun more than I did anything, because that tree is the only one that's causing me any problems. But by doing that shading model, it actually has changed my output of production from about 6,000 kilowatt hours a year to 54, well, about more like 5,700 kilowatt hours a year to 5,400 kilowatt hours a year. And that's very accurate to what I'm actually producing. And so it's doing the computations right now to do that 3D shade. That's a really fun tool. Be careful with it because you can overestimate shading. If you click on it, mess with it, do something wrong, you can actually be estimating really a lot of shading accidentally. So you got to be a little careful. In using it to make sure that you're using it right. I've seen that example a few times where people open the shading tool, didn't really do anything in there, but then it still estimated some shading losses because of it's still turned on and they don't have it quite set right. So use it with care, but it can be a powerful tool. The most powerful tool for estimating shading though, honestly, go visit the site and stand where the solar is going to be and just visualize the sun moving across the sky. There is not much that can replace going and visiting the site. And honestly, there are solar installers that love to give you a quote without having ever visited the site. That's a problem. That's a problem. Okay, I'm done for today. Let's open it up for questions. And I'm going to reopen my original project that we started messing with, and we'll just go to any questions you guys have.
And if you have a question, feel free to unmute yourself and just ask your question live. It's a relatively small group here.